In this section, we will demonstrate the setup and acquisition of Auger depth profiles. The microwave transistor is not a suitable sample for demonstrating Auger depth profiling. So we have mounted a new sample, introduced it into the system, and have positioned it at the focal point of the analyzer. Let's now prepare the system for depth profiling. The first step in preparing the system for depth profiling is to differentially pump the ion gun. That is, we want to be pumping the ion gun with the turbo pump. That is controlled with the auto valve control. Right now, all of the valves on the auto valve control are closed, indicated with red lights. What we would like to do is press the differentially pumped ion gun button, which will then open the valve between the ion gun and the turbo pump. When we press that button, there is a time delay. The thermocouple valve is measuring the vacuum in between the turbo pump and the ion gun, making sure that we have adequate vacuum before we open valve 4. We now see that valve 4 is open, indicated with a green light. If we do not have proper vacuum between the turbo pump and the ion gun, since the ion gun is in the main chamber, if the valve were to open, we could let the system up to air. This, once again, is an interlock feature where the differentially pumped ion gun button will not activate that valve unless we have proper vacuum. Next, we want to admit gas into the system using the variant leak valve located on the ion gun. We turn in the counterclockwise direction as we monitor the pressure on the digital gauge control, which is located in the second bay under the tabletop. Here we can demonstrate both. We turn slowly because we do not know exactly how the leak valve will react. Once we start seeing the pressure rise, we then want to turn the leak valve even slower. Each leak valve is different as to the number of turns before we start seeing the gas being admitted. Now we see the pressure rising, so we are admitting gas into the system. Since we have a thermal valve control, to set up for the thermal valve control, we want to admit gas to an order of magnitude higher than the pressure at which we will be sputtering. Most of our sputtering, because we are differentially pumping the ion gun with the turbo pump, will occur around this pressure, low 10 to the minus 8 range. So to set up the thermal valve control, we want to be an order of magnitude higher. So we will admit gas to approximately 1 times 10 to the minus 7. You can see that as I turn it counterclockwise, we are admitting more gas, and a little bit clockwise, and we start closing the valve. So we will leave the valve set in this position, giving us a pressure of low 10 to the minus 7 range. With the leak valve set, we are now ready to obtain the proper settings on the Balzer's thermal valve control. That is located in the third bay under the ion gun control. Two of the switches which we do not use on the thermal valve control is the reset time and the prop gain. If you want to learn their function, please refer to the instructions for the Balzer's thermal valve control. We will set them a reset time of approximately 5 minutes, and the prop gain we will leave set at approximately 15 in between the 10 and the 20. At this point, we are ready to turn the thermal valve control main power on. And we also want to make sure that the toggle switch between limit and set point is in the limit position, and that the limit potentiometer is turned completely counterclockwise. Monitoring the pressure on the digital gauge control, we now want our limit to be approximately in the 10 to the minus 10 range, monitoring the digital gauge control. So as we turn clockwise, we are applying a voltage to the thermal valve control, which will then allow us, as you can see, to close that leak valve. We want to close that leak valve so that when we stop pumping the ion gun with the turbo pump and introduce a sample, we will flip the switch to limit, and it will automatically close the valve for us. The setting for our limit pot should be somewhere close to 10. You can see that we are now in the high 10 to the minus 9 range. So we will set the limit pot at approximately 9, which looks like that should, in essence, close our leak valve. At this point, we're ready to set up the ion gun control that is located in the third bay directly under the tabletop. Before we turn the main power to this unit on, we want to make sure that we have no emission current going to the filament, or we can shock the filament with current. It's very possible that we could, in doing that, burn the filament out. So let's first make sure that our meter is toggled to the emission setting. We want our emission scale to be toggled to ×1. We then want to make sure that the emission pot is turned fully counterclockwise. We are now ready to turn the main power on. The power switch is located on the left side of the ion gun control unit. I have already calibrated the ion gun, and I now want to obtain the proper settings for this depth profile. Those settings have already been predetermined in the calibration section of the videotapes. We want to make sure that the ion gun voltage will be controlled by the computer, so we want the toggle switch for beam voltage to be in the remote position. I also want to make sure that my beam voltage is at 3.5 kV, because that is where I have the calibrated settings. Next to the beam voltage, we have the condenser lens and objective lens. Once again, I have obtained calibrated settings for those. I want to make sure that my condenser lens for this depth profile is set at 4.0, and that my objective lens is set at 3.65. The XY position pots have been locked during calibration in order to align the ion beam. Those I want to leave in the locked position. I have determined that for the proper sputter rate on this particular sample, we would like to use a raster size of 3 by 3. So I will set the X and Y raster size pots at 3 and 3. We also want the raster drive to be activated. We have an external and an internal activation. External means that the raster drive will be controlled by an external source. For example, if we had a SIMS unit, since we do not, we will not use the external raster drive, but we will drive the raster internally. So we want to make sure that the toggle switch is set on internal. We are now ready to apply current to the filament. We again want to make sure that the meter is measuring the emission to the filament so that the toggle switch is in the emission position. We also want to make sure that our emission scale is on ×1. We are now ready to turn the emission pot clockwise, and we can monitor then the emission through the filament. The proper setting is 25 milliamps. We now have 20. And we are now set at 25 milliamps. It's very critical that we're set at 25 milliamps so that we get a proper pressure reading when we toggle the meter switch to the pressure position. It is all based on 25 milliamps. So it's very critical, again, that at this point we have the emission scale of ×1 and an emission setting of 25 milliamps. My ion gun does not have a getter pump, so I will leave that in the off position. If you have a getter pump, at this point the getter pump position switch should be in the run position. Applying current to the filament, as we have done, will initialize the analog feedback voltage to our thermal valve control. In order to set the thermal valve control, we now want to make sure that our meter switch is toggled to the pressure position. On our split screen, we can now see both the meter from our ion gun control and the set point potentiometer from our Balzer's thermal valve control. We are now ready to set the pressure in the ion gun using the thermal valve control. First, we need to make sure that the potentiometer is turned counterclockwise to 0. We can then toggle the switch to the set point position. As we turn the potentiometer in the clockwise direction, we will see an increase in pressure. Monitored on the meter on the ion gun control. We want to regulate that pressure to about 15 times 10 to the minus 3 pascals. We see now that we have a pressure indication. Slowly rising, we now have 10. Let's turn the set point down a little. Again, once we regulate this to the proper position, it will be reproducible every time we put the toggle switch to the set point position. We now have approximately a setting of 15. Now that we have the proper ion gun parameters, let's return to the computer and set up the electron gun for Auger depth profiling. To locate an area on the sample, we used our initial settings for the scanning electron microscope, those settings being 3 kV and a magnification of 100x. We were then able to locate the sample on the sample holder, also locate a spot on the sample, and then find the focal point of the analyzer using the align routine. The sample we are analyzing is a chromium on copper sample. The chromium is probably oxidized on the surface with some carbon also present. What we would like to do is set up the electron gun for the depth profile and then first obtain a survey scan to find out exactly what is present on the surface. Since the sample is a relatively flat sample and is uniform, we do not need a small beam for the analysis. What I would like to do is use about 3 microamps of current so we get good signal to noise to demonstrate the profiling routine. I would also like to use 10 kilovolts of beam voltage, again so we get good signal to noise and we can more easily see high energy transitions. Let's start by changing our beam voltage, function key number 9, and entering a beam voltage of 10. We can now use the auto video, soft key number 2, in order to reset our secondary electron multiplier. I also want a high current. Since I'm not concerned about the beam size, I'll change my objective lens aperture to the largest aperture, that being the 93 mil aperture. Again, we have an increase in current, so I will utilize the auto video to reset the secondary electron multiplier. What we can do now is measure the beam current. So I will toggle function key number 15, my beam current reading to on, and we will monitor the beam current reading on the status line. Pressing function key 15 and toggling it to on will activate the beam current reading. We now see that we will get an indication of our beam current with these parameters. We have a beam current right now of approximately 1.3 microamps. We would like, as I had mentioned, somewhere between 3 and 5 microamps. So we will change the condenser lens. Pressing function key 14 allows me then to slew the condenser lens. I will then slew the condenser lens down, opening the condenser lens, and monitor the current. We now have 3.45 microamps, which would be sufficient for this analysis. I can now toggle my beam current reading off by pressing function key 15 and toggling to off. We will then see that my beam current reading will be entered as approximately 3.43 microamps of current. Once again, since we have more current, I want to press soft key number 2, which will activate the auto video and reset our secondary electron multiplier. Going to the TV screen, we are at 100x magnification. What we need to do now is bring that into focus. I know I will need to coarse focus, which is function key number 10, and then I will slew the focus until I get a sharper image. I can then use the fine focus and bring the sample into focus. As you can see, it's a relatively flat sample with no features except for possibly some dust particles on the surface. What we will do is change the magnification to 1000x. Again, we see very few features. We can bring it again into sharper focus. We do see a feature here and a feature here. We would like to analyze possibly in the center with no features included. So let's change the magnification to 30,000x, where we now see no features, but we will be rastering over this full area. Since we will be sputtering, we do not want to saturate the secondary electron multiplier when the ion gun is on. So going back to the computer terminal, we would now like to go to the next menu using soft key number 6. And we want to toggle our SED multiplier to off using function key number 3 and toggling the SED multiplier off. We now have our electron gun set for analysis, so we can exit the SEM menu. Before we begin analysis, since we have a new sample, we would like to change the file naming. To do that, we press soft key number 7, labeled File Naming. Our last sample was our microwave transistor. We used the sample file prefix MWT. We started with a file number of 101. We now have a file number of 109, meaning that we have data of MWT 101 through MWT 108. Since this is a new sample and we are demonstrating profiles, let's use a sample file prefix of PRO for profile. Since this is our second sample, let's use a 200 series, starting with 201. And for comment for this sample, it is a chrome on copper sample. We can now exit the file naming menu. Let's begin with a survey scan. We have already discussed that in the survey scan part of the videotapes. So we can enter the survey scan setup menu mode by holding the shift key and pressing function key number 5. We can use the previous settings and edit them as necessary. We have a lower limit of 30. Let's change our upper limit to 2030, so we have exactly 2,000 data points. We can go 1 EV per step. Since we have a higher current, we do not need 10 minutes per area. Let's go with 5 minutes. Excuse me, I typed 6. Let's change that to 5 minutes, giving us a number of cycles, 10. We also do not want selected areas. We want the full area at 30,000x, which we set up in our SEM menu. So we can toggle using function key number 6 and toggling analysis area to full. Our EMS routine is set at 1 point. Let's toggle that to sample to make sure that there are not areas in that 30,000x area of analysis that might have a higher concentration and might set the multiplier voltage improperly. Once again, the safest EMS routine mode setting would be in the sample mode to assure that we do not saturate the Auger multiplier. Function key number 7 and toggle to sample. We are now ready to acquire the survey scan. We can do that by pressing soft key number 1. We are now setting the multiplier, and the Auger analysis has begun. Notice our file name is PRO201. We are now looking at cycle 2 of 10 cycles. We are doing a full area analysis, this being the one and only area. So we are analyzing area 1 of 1. When setting up for the profile, it's important to know something about the sample, what elements you want to follow as indicated on the surface, which we are now monitoring, and also we need to know what the substrate is. We need to include that in the profile, so once we sputter through the material on the surface, we will be able to monitor the substrate material and know when we are into the substrate, thus telling us that we are finished with the depth profile. We also need to be aware of any possible contaminants that we might be looking for. This is a chromium on copper. It's very possible that at the interface between the chromium and copper layer there might be a suspected contaminant. If we are not sure of what that contaminant might be, what we can do is utilize the suspend profile routine and obtain a survey scan at that interface. If we suspect an element, we can set up for that element and monitor through the profile from the surface into the substrate and determine if at any time during the profile we were able to detect the presence of that element. These things need to be planned ahead of time before we set up for the profile. Once we set up the elements we are going to follow in a profile, we cannot add or delete any elements once the profile has begun. So it's very important to know the sample and understand what exactly we are looking for, and also the possible concentration of those elements in which we are looking. It's very possible if we are looking for low concentrations of an element, we then need to spend more time looking at that region than we would for the major elements. We need to determine the number of sweeps for each element. If we suspect a contaminant that may be at low concentration, we then need to spend more sweeps looking for that suspected contaminant. Or if we know something is there but at a very low level, we also need to spend more sweeps in order to get good signal to noise for that element. Once again, these things we need to determine ahead of time. We are now presently on cycle number 10 of 10, meaning this is our last cycle. When this survey scan is finished, what we will do is display and differentiate in order to evaluate what elements are present and what elements we wish to include in the profile. The survey scan is now complete, and we return to our home bank. To display the survey scan, we press function key number 16, which will display last acquisition. This is our survey scan from the surface of this sample. What we would like to do is differentiate this. So let's enter the data massage bank by pressing soft key number 5. We then want to use function key number 23 to toggle to the next bank. We now can differentiate by pressing soft key number 7. This is now our differentiated spectra. We see that on the surface we have carbon and oxygen. The oxygen is located between the two chromium peaks. We also have copper, and we see some indication of silicon. From the survey scan, we also want to determine, once again, the ratios in order to give us statistical information for setting up for the profile. For example, if chromium is my major peak and silicon is a very, very small peak, then if I go one sweep on the chromium peak, I need to go many sweeps on the silicon to get similar statistics. From this, what we can do is, for example, go 3 sweeps on oxygen, 3 sweeps on chromium. We know that the substrate is copper, so once we get into copper, it will also be very strong, so we'll go 3 sweeps on copper. Most likely, carbon is only on the surface and will decrease, but we want to be sensitive to the carbon because it's possible that there is a carbon contamination between the chromium and copper layer. So let's go 10 sweeps on the carbon, and the chromium being very weak, we will go 20 sweeps. These things we need to determine before we set up for the profile. That's why it's good to take a survey scan, evaluate what is present, and also the amounts of what is present, and also think ahead as we sputter into the sample that carbon will decrease, oxygen will probably decrease, copper, being the substrate, is sure to increase. We're not sure about silicon. If that's a contamination, it might be only on the surface in small amounts, or it's possible that it's a contamination all the way through. In either case, we probably want to be sensitive to silicon, thus meaning we need to go several sweeps on the silicon peak. We can now erase the screen, holding the control key and pressing the clear. And let's enter our profile setup menu by holding the shift key and pressing function key number 7. Once again, we can use previous settings, new settings, or call a file from the disk. We want to use new settings. Enter. With a profile, we can do a window profile, which is very similar to our multiplex, where we set up a region and we monitor the complete peak within that region. We could also do a 2-point profile, very similar to setting up for maps and line scans, looking at the peak minus background, background being defined by 1 point, or a 3-point profile, which would be again similar to a 3-point map or a 3-point line scan setup, that being 2 points defining the background and 1 point defining the peak. What we would like to do is first demonstrate the window profile. Once we are finished, we will come back and, using the same sample, set up for a 2-point profile. The advantages and disadvantages are, with a 2-point profile, you are looking only at 2 data points. Thus, you can spend many sweeps and get good signal to noise. Whereas in a window, you are normally looking at several data points over a region. For example, a window which is 30 electron volts wide, and we are looking at 1 volt per step. That is 30 data points per window. With a 2-point profile, we are only looking at 2 data points. If we need to, for example, go 3 sweeps on the window, that is 90 data points. If we want 90 data points on a 2-point profile, we can use 45 sweeps. With 45 sweeps, we get much better signal to noise. So there is definitely advantage time-wise and signal to noise using the 2-point and 3-point profiles. The disadvantage in the 2-point and 3-point profiles is that if the peak shifts slightly, we cannot adjust for that shift. Whereas the window will allow us to monitor the peak and background with some leeway, because we normally set the window a little bit wider than the actual peak itself. Also, a disadvantage to the 2-point and 3-point is we do not have sensitivity factors for the N of E spectra. Therefore, we cannot generate atomic concentration information from a 2-point or a 3-point profile, but we can from the window profile. With these things in mind, let's set up a window profile first, and when we are finished, we will set up for a 2-point profile. Striking the Enter key now allows us to set up our windows for the elements which we wish to follow. The first element we will follow is the carbon peak. When we enter carbon, automatically, once again, the parameters will be entered from the element table. Also, automatically, we choose the narrow acquisition window, meaning that our acquisition window, which is line 5 and 6, will be from 257 to 287. Coincidentally, the analysis window will be from 257 to 287. What this means is we will acquire an energy range from 257 to 287, and the analysis will be within that range. We can change the narrow acquisition to no by typing in N and enter. What will happen is our acquisition window is no longer narrow, but it is wide, and the wide acquisition parameters are from 245 to 295. Our analysis window is still from 257 to 287. This gives us the flexibility that if the peak shifts, we have a wide enough window that we can alter the analysis window if necessary in order to compensate for any peak shifting during the acquisition. If we leave the narrow acquisition window, then we can only change the analysis window within those limits. We do not have more data to work with. Now, for example, if we find that the lower limit of carbon is not at 257, after the analysis we can do a profile redefine, and we can redefine the analysis window to a lower limit of as low as 245, which is now our acquisition lower limit window. What I would like to do for this window profile is make sure that our acquisition window is wide so that we can demonstrate the profile redefine routine. Line number 9 allows us to use 1 volt per step. We can change that if we want to. If we need more peak definition, we could use a higher EV per step. For example, we could use 0.5 volt per step. That would give us more data points and would give us a higher peak resolution. But again, most of the acquisition for carbon should be done with 1 volt per step, because when we go to 0.5 volt per step, it then takes twice as long to acquire this same window. We are spending 25 milliseconds per step, going now a range of 50 electron volts. That means 50 data points. If we were to change the EV per step to 0.5 volt per step, that would then be 100 data points at 25 milliseconds per step, which increases the depth profile time. So again, it depends upon the analysis, and it depends upon exactly what you are looking for. If you can sacrifice the time and spend more time, you can use a smaller EV per step and get better peak resolution. But that would only be, for example, if we were looking at a silver peak where we need peak resolution, or if we were looking at the difference between silicon oxide and elemental silicon. Once again, we would need better peak resolution. For most applications, 1 volt per step is sufficient. We will then use a 5-point differentiation. When we calculate the atomic concentration, as in the multiplex, we can use the 5-point differentiation, measure the peak-to-peak height, and thus attain the atomic concentration. We also mentioned that the number of sweeps on carbon we would like to set at 10, and it just so happens that it is preset at 10 sweeps. We now have the correct parameters for the carbon region. We can now add another region by pressing soft key number 1. The second region will be the oxygen peak. Once again, we do not want the narrow acquisition. We would like to say no to narrow, which will give us then the wide acquisition parameters. Again, I had mentioned the EV per step. Since oxygen and chromium are very close, we may want to leave 0.5 volt per step, give us more data points, so that we can easily distinguish between the oxygen and the chromium. We had also mentioned that the number of sweeps for oxygen should be set at 3, so by pressing function key number 11, we can change the number of sweeps to 3. We can now add another region, which will be our chromium peak. We will look at the CR2, the second chromium peak. Once again, let's use wide acquisition parameters, saying no to the narrow acquisition parameters. And we also would like 3 sweeps on chromium, function key number 11, and change the number of sweeps to 3. Soft key number 1, add another region, the copper peak. CU1 would be the main copper peak located at 920. Again, let's use the wide acquisition parameters, saying no to narrow, and also 3 sweeps on the copper. And we can now add our last region, that being silicon, the Si2 peak. Again, the wide acquisition parameters, saying no to narrow, and we want 20 sweeps, function key 11 and 20. We are now ready to go to the next menu now that we have the proper parameters and number of sweeps which we predetermined for these elements. We could also, as we could with the multiplex, delete any of these regions or change any of those parameters. Just to review that, if we wanted to change a parameter for oxygen, to get to that region, which is region number 2, we would hold the shift key and press function key number 2. That then allows us to press any of the other function keys. For example, EV per step would be function key number 9. We could then change that parameter for oxygen. Also, we could delete any region using soft key number 2. We first toggle to the region we wish to delete using the shift key and the function key corresponding to the region selection number. For example, copper, shift key, function key number 4. If we then pressed soft key number 2, we would delete the copper region, and our analysis would be done on carbon, oxygen, chromium, and silicon. Again, now that we have the parameters entered, we can go to the next menu by pressing soft key number 8. We now see page 2 of the profile setup menu. The first thing we need to enter is sputter time. On this sample, the depth is somewhat unknown, so let's start with a sputter time of 20 minutes. Once we are finished with 20 minutes, if we need to do more, we can utilize the more function, which is function key number 12. If we find that our profile is finished before 20 minutes, we could then utilize the cycle stop and stop earlier than 20 minutes. We do not have to go only 20 minutes. We can either stop earlier, or once the 20 minutes is completed, we can use the more routine and spend more time on the profile. The second line, we then have to choose our sputter mode, whether we want to do a continuous depth profile or an alternating depth profile. Typically, if we have electron beam current of less than 1 microamp, we will use the alternating sputter mode. When the ion gun turns on, we can saturate the Auger detector mode, even in the V to F, if we are below 1 microamp of current. We can get interference from the ion gun. So normally, less than 1 microamp, we always use the alternating mode. If we are monitoring a lot of elements or multiple areas, we also want to use the alternating mode, because the continuous means that we are always sputtering, and by the time we get back to the first element, if we have many elements, or by the time we get back to the first area, if we have many areas, we could be very deep into the sample and miss some of the interface layers. Since we are going 20 sweeps on the silicon and several sweeps on carbon, and we have 5 elements that we are monitoring, for this particular analysis, it would probably be best to use the alternating sputtering mode. What we will do is when we redo the profile utilizing the 2-point method, we will do that profile using the continuous mode. So let's demonstrate the alternate sputtering mode. We can then press function key number 2 and toggle to alternating, and then enter that. Once we choose the alternating sputtering mode, we need to determine the sputter interval. If our sputter interval is every minute, then in 20 minutes we will have 20 data points, meaning we will sputter for 1 minute, then collect data on the carbon, oxygen, chromium, copper, and silicon peaks, sputter another minute, and then collect data again. That would be 1 complete cycle. Depending upon the thickness of the layer and the sputter rate which we have set up, we need to determine the sputter interval. What I would like to do is monitor the sample every half minute. So let's change our sputter interval, function key number 3, change that to 0.5 minutes. That then updates the number of cycles. In 20 minutes, if we monitor every half minute, it will take 40 cycles. Line number 4, save energy regions every nth cycle. If we want to do a profile redefine, we must save every single energy region. That means n must equal 1. If we are not concerned about a profile redefine, and we have a long profile, for example, possibly a profile that would take several hours, and we have several hundreds of data points, we can fill up a disk very quickly. What we then want to do is possibly save every nth region, for example, every 5th region. What this does is actually saves the window profile. It actually saves every region depending upon the nth cycle that we enter. The peak-to-peak height of each region will still be displayed and stored. So if we have 100 data points in the profile, we will see peak-to-peak heights for 100 data points. If we change the every nth cycle to 5, what we will then do is have a energy region that we can call up and look at the peak itself, the peak shape, for, again, only a window profile. We can call up that energy window for the 5th cycle, the 10th cycle, the 15th cycle, the 20th cycle, and so forth, out to 100 cycles. By saving every region, we can look at cycle number 1, 2, 3, and so forth, out to 100 cycles. So you see that it takes more data space, more memory space, to save every cycle than it would every nth cycle other than 1. Again, since we want to demonstrate the profile redefine, we want to make sure that our energy regions, the nth cycle equals 1. Line 5 is our region display mode. In doing a window profile, we can either monitor the peak-to-peak height of each element or we can actually look at the region display and look at the actual element peak as it is being acquired. When we look at the region display, we can monitor that either in the N of E mode or the differentiated mode. Once we enter the region display mode, we also at that point have a choice between the N of E or the D N of E spectra. So it really doesn't matter at this point whether our region display mode is in the N of E or D N of E. We can toggle back and forth on the fly while we are taking data. Line number 6, our differentiation points. Once again, we want to be at 5. If we have real low current and a 5-point differentiation is noisy, we could change that to 7 or 9, which would give us a smoother looking spectra. Here we have a lot of current, so we will leave the differentiation points at 5. Number 7, the analysis area. Again, we want to do a full analysis and not selected areas. We have it set up at 30,000x, looking at the full area, so we will toggle to full. And line number 8, the EMS routine, we want to toggle to sample mode so that it sets up the multiplier averaging over that 30,000x area. At this point, we are ready to test acquire to make sure that our windows are set up properly. This test acquire, once again, is very similar to the test acquire which we demonstrated in the mapping routine and in the line scan routine. Pressing soft key number 2 allows us to enter the test acquire menu. Once again, our first element is our carbon. We have the wide acquisition window, which is from 245 to 295. The number of sweeps we are monitoring now is 1. Let's change that by pressing function key number 4, and let's go 10 sweeps on the carbon. We want the acquisition area to be full. What we would like, though, at this time is to display this in the differentiated mode. That is where the peak-to-peak height is calculated for the depth profile. When we monitor the profile itself, it is in peak-to-peak mode, and the peak-to-peak is a differentiated peak-to-peak signal. It looks at the window, differentiates the N of E data that is in that window, and from that differentiated spectra measures the peak-to-peak height and plots that as a function of depth. So we want our display to be differentiated. Function key number 6 and toggle to dN of E. Function key 7, we want our differentiation points to be 5. We are now set to test acquire, which is soft key number 1. We now see the carbon peak. What will be displayed in our peak-to-peak height is the positive most excursion and the negative most excursion. That will be our peak-to-peak height. That is why we want to go through the test acquire, is to make sure that our window is wide enough to include both the positive most excursion and the negative most excursion. Notice that if we would have used the narrow acquisition parameters, they were from 257, we would not have included our positive most excursion. Thus, we would have gotten an improper or an incorrect atomic concentration calculation. It would have calculated using this peak-to-peak height, but it is not representative of the true amount of carbon on the surface of this sample. Since we are satisfied with the lower limit and upper limit of this window, we can now monitor the next element by pressing soft key number 5. This will now be looking at oxygen. We still want the full area and the differentiated, so we can press soft key number 1 and test acquire. What we see here is the oxygen peak, and on either side we see the chromium peaks. That means that our window is actually too wide. We are including the chromium peaks, but with the profile redefined, after the profile has been acquired, we can change the acquisition window to include only the oxygen peak. So I would like to leave the window this wide so that we can more easily demonstrate the profile redefined. We're now ready to test acquire our next element, pressing soft key number 5, our next element being chromium, and soft key number 1 to activate the test acquire. Once again, we can easily see the chromium peak. We also see the oxygen peak, but it will not influence the peak-to-peak height of chromium. So we can leave the window once again at the width we have it, with a lower limit of 495 and an upper limit of 555. Let's look at the next element, which is copper, and test acquire. We see our copper peak positive most excursion here, negative most excursion here. We have quite a bit of area where we have no signal contributed to the peak. That is actually a waste of time to acquire this data. So what we can do is we can change the lower limit from 875, for example, to 900. And we can leave the upper limit at 935. Let's now reacquire and see if the peak fits within that energy window. We see that the peak fits nicely. We are not losing any information. And it will be quicker to analyze this window now than using the wider range. So again, we can use the test acquire to help us define our lower and upper limits so that we do not waste time during the profile. Let's look at our next element, our last one, being the silicon. Test acquire. We see that we do not have a lot of silicon present. The more times we sweep, the better the signal to noise. It looks like we have an appropriate window. the lower limit being 1590 and upper limit being 1635. So we can leave the lower limit and upper limit for the silicon window. Now that we have all of our windows set properly for the depth profile, we can begin acquisition of the profile by pressing soft key number 6. This display is the peak-to-peak height of each element. What we can also do is look at our region display by pressing soft key number 5. Notice that now soft key number 5 is profile display, which will take us back to the peak-to-peak height of our profile. We are monitoring our elements now in the NV mode. To monitor them differentiated, we can press soft key number 6. We also see now the difference between the acquisition window and the analysis window being indicated by the 2 white bars. When we see our peak-to-peak data, it is taken from the window in between the 2 white bars. At the end of the profile, we can then redefine that region, that analysis window, if need be. We see that with the carbon peak, we will have to redefine. Because the carbon peak, this is now the silicon peak, but we'll notice when we come back to the carbon peak, we can also see actually on the silicon peak that we will have to redefine the negative most excursion. The peak is actually not within our analysis window. It is within our acquisition window, but not properly defined by the analysis window. We need to bring the upper limit of the analysis window, it looks like probably to 1630. We have now begun sputtering. This is now our 3rd cycle. We go 2 full cycles before we actually begin sputtering. That is our pre-sputter data information. We are now on cycle number 3 out of 42 cycles. To go 20 minutes, as we mentioned, would be 40 cycles with 2 cycles for the pre-sputter. That is automatically then figured in that we will go a total of 42 cycles. We are right now on cycle number 3, and we are monitoring region number 5. We can toggle back to our profile display by pressing soft key number 5. This will once again give us the peak-to-peak height information. Notice we had a large amount of carbon on the surface, which has now decreased because we have sputtered some of the carbon away. We can also see that copper, which is our purple line, was higher on the surface and has now decreased. Chromium, which is our blue line, has increased because we are now going further into the chromium layer, which is located on top of the copper. Looking closer at the top of the graph, we see that the file is stored under the file name PRO202. Remember that our PRO201 was the survey scan. We are looking at a full area. Presently, we are on cycle number 5 out of 42, where also the last region which was displayed was silicon. We now see that we have displayed region number 1 out of 5, which is our carbon. Now we've displayed region 2 out of 5, which is our oxygen. This is now for cycle number 6. Region 3, which is chromium. Region 4, which is copper. Notice also that at the moment our ion gun is off because we are acquiring data. What will happen is when we finish acquiring the data, the ion gun will then toggle on for 30 seconds, which we had asked it to do. We notice now that our ion gun is toggled on. It has just toggled off. When we see the ion gun come on, it will be on for 30 seconds. We are then monitoring, as we mentioned, in 20 minutes. We are monitoring every half minute, thus giving us our 40 cycles with the 2 cycles pre-sputter. Once the ion gun shuts off, we then begin data acquisition. Cycle 7, region 3. Cycle 7, region 4. Once we display region 5, we'll then be able to see our ion gun toggle on. So again, with alternating sputtering, we turn the ion gun off, collect the data. Once we are finished collecting the data, we then toggle the ion gun on, in this case for 30 seconds. Once the 30-second sputtering period is finished, it then toggles the ion gun off and again starts collecting the data. We can also press soft key number 5, our region display. When the ion gun is on, we will not be able to toggle from the profile display to the region display until we have finished sputtering. Once we finish sputtering, we will then toggle to the region display. In the region display, we see that we are presently on cycle number 9. This is region 1 of 5. We also see the number of sweeps as it displays the data. That is sweep 3 of 3. We also went 3 sweeps on region 3, which is chromium. So notice we are updated on not only the region, but the number of sweeps we are displaying for that particular region. Silicon, we asked for 20 sweeps, and we can see which sweep number is being displayed. It does not display them sequentially because it takes more time to display them, to acquire them. So what we do is we give preference to acquiring the data, and we will then, for example, as we saw here, we will display sweep number 3, then sweep number 7, possibly sweep number 8, then sweep number 10, depending upon where we can interrupt the acquisition. Again, priority is given to data acquisition So we will display a sweep that does not interfere with the acquiring of the data. Once again, we can toggle back to the profile display by pressing soft key number 5. And continue to monitor the peak-to-peak heights of the elements as a function of time. Once the profile is finished, we return to the home bank in order to display the profile and evaluate it. We once again use the function key to display acquisition, which is function key 16. That allows us then to enter the profile display menu, the file name being PRO202. We only have one area. We can either display profiles or the regions. We do have 5 different regions, 5 different windows. If we wanted to display those windows, we would toggle the mode to region. Line number 3, we can also, in the profile mode, display any of the regions separately, the peak-to-peak heights, either separately or all of them at the same time. These various ways of displaying the profile will be discussed in the data massage section of the videotapes. What we would like to look at is the profile and all regions, which is where the profile display menu defaults to. We can now display the profile by pressing soft key number 1. We see the interface where we have gone from the chromium into the copper. We also see that carbon and oxygen appear to be present throughout the chromium layer and then disappear once we get into the copper layer. The interpretation and evaluation of this information will also be covered in the data massage section. What we would like to do now is set up for this same profile, not using the window mode, but using the 2-point profile mode, and also, instead of using alternate profile, using continuous profile. To demonstrate the 2-point profile mode, we have repositioned the sample and will begin acquisition on the new area. Since we are on a different area for the same sample, let's first begin with our file naming using soft key number 7. We can keep the same sample file prefix and also the same comments, but let's change our start file number, pressing function key number 2. Since this is a new area, let's begin with a 300 series, so we will start file number 301 and enter. We can now exit the file naming menu, soft key number 8. We already have our survey parameters set up from our first survey scan. Since this is a new area, there might be some material present here that we did not find on our first area. So let's begin with a survey scan by pressing function key number 5. We can avoid entering the menu. Once again, we have the parameters set up. By pressing function key number 5, the survey acquisition will begin. We are now on cycle 8 out of 10 cycles. The electron gun parameters for this survey scan is the same as our first survey scan and our first profile. We are at 10 kV with 3.43 microamps of current. We are also at a magnification of 30,000x, exactly where we acquired the first survey scan and profile. And we are acquiring this in the full acquisition mode. We are now on cycle 9. One more cycle and we will have completed our 5-minute survey scan. Once again, when the survey is finished, the screen will go blank. We will want to redisplay this survey scan and differentiate it to find if there are any new elements present in this area that we did not see in the first area. The survey is now complete. To redisplay the survey scan, once again we use function key 16. Pressing soft key number 5 allows us to enter the data massage banks. We see that our differentiate routine is using soft key number 7. That will now activate the differentiation. We now see the differentiated survey scan. Once again, we see the chromium and oxygen present. We see a smaller amount of copper than we saw on the first area. We also see carbon, possibly an indication of sulfur being present, and also possibly some nitrogen present. Very, very low amounts, probably only surface contamination. We do not see any evidence of the silicon present. We also noticed from our last profile that the silicon was quite constant all the way through. If it was there in very low amounts. So I think for this profile, we will eliminate the silicon peak and not follow that peak. We will once again set up for carbon, oxygen, chromium, copper, but we will not use the silicon peak. We can now clear the screen by holding the control key and pressing the clear key. We can then enter the profile setup menu by holding the shift key and pressing function key number 7. Since we essentially will be using the same elements, let's use the previous settings. So we can hit enter. That will give us our previous settings. What we want to do is not do the window acquisition method, but the 2-point. So we can toggle using function key number 2, acquisition method to 2-point, and enter. That will now automatically fill in our region selection with peak and background energies using the same number of sweeps that we used for the window acquisition method. We mentioned we do not want to follow silicon, so to delete the silicon region, we will hold the Shift key and press function key number 5, that is the region selection number. We can then delete that region using soft key number 2. We had also mentioned earlier that during a window acquisition, we look at a number of data points. Therefore, it slows down the acquisition. We will now be looking at only 2 data points, peak and background. So what I would like to do to increase the signal to noise is we will triple the number of sweeps for each of the elements. Let's begin with carbon. Using the Shift key, pressing function key number 1 allows me to change the carbon region selections. Changing the number of sweeps is function key number 6. And let's triple that and go 30 sweeps on carbon. Shift function key number 2 allows me to change the oxygen parameters. Function key number 6, number of sweeps 9. Shift function key 3, function key number 6, number of sweeps 9. And for copper, Shift function key number 4, function key number 6, and 9 sweeps. We are now finished with the 2-point peak and energy setup. We can now go to the next menu, which is soft key number 8. Again, we will sputter for 20 minutes, but we now want our sputter mode to be continuous rather than alternating. So pressing function key number 2 and toggling the sputter mode to continuous and enter. Notice that with continuous, we do not need to choose the cycle time. One cycle will be 30 sweeps peak minus background for carbon, 9 sweeps for oxygen, 9 for chromium, and 9 for copper, whatever amount of time that takes. During the acquisition, we will be sputtering. Remember, in the alternating mode, we would sputter for half a minute, stop sputtering, and acquire the data. With continuous, we will be acquiring the data while we are sputtering. We again want our analysis area to be full and our EMS routine mode to be set on sample. As in the maps and line scans, we are not exactly sure where our peak and background energies are. To determine them, we need to enter the Test Acquire menu. Test Acquire is soft key number 2. Our first energy window will be for carbon. Very similar again to the map and line scan Test Acquire. We have a peak energy of 263 and the acquisition width will be 50 electron volts. We will again look at a region in order to identify where the peak and background should be set for this particular element, being carbon. Once again, we would also like to change the number of sweeps. So pressing function key number 5, let's once again go 20 sweeps on carbon in order to increase our signal to noise. Our acquisition area selection will be full. That's where we will be doing our profile itself on a full area. So we can duplicate that in our test acquire mode. We also want it to be displayed in the NAV because now with our 2-point profile, it will be the peak height of the NAV data. That is the peak energy minus the background energy of NAV data. We are now ready to test acquire, pressing soft key number 1. We see that our background energy is actually set further out than what we are displaying and acquiring the data. The upper limit of our data acquisition in the test acquire is 288 electron volts, and our background energy is set at 293. Since we only have a carbon peak that we determined from our survey scan, we know that there will be no interference peaks above 288, so we can leave our background energy at 293, but we should change our peak energy, finding the maximum counts occur at 265. So we can change peak energy, function key number 1, from 263 to 265. We now have the proper peak and background energy for carbon. Let's go to our next element using soft key number 5. We are now looking for oxygen, 20 sweeps, full area, NAV mode. We can test acquire, soft key number 1. This is an excellent demonstration for the need for test acquire. Notice that our peak for oxygen is set at 503. Actually, it should be closer to 510. Also notice we are getting interference from the chromium peaks, both on the left side and the right side of the oxygen peak. Notice also that our maximum counts says that the energy is 475. That is actually an interference from our chromium peak. What we need to do is choose closer to the center of the oxygen peak, probably 508 as a center. We then want a very narrow width so that we can eliminate interference from the chromium peaks. If we choose 508, we see that roughly 516 would eliminate interference from the higher energy chromium peak. So with a center of 508, if we went 20 electron volts, we would go up to 518 on the right side and down to 498 on the left side. Let's change our peak energy to 508. And let's change our acquisition width, function key number 3, to 20 volts. And let's reacquire the test acquire using soft key number 1. Now we see that the maximum counts energy is indeed coincidental with the peak of the oxygen. We can also see where the background energy should be, not at 535, but most likely at 517 electron volts. That would be our negative most excursion. Again, the energy is at 509, and from this test acquisition, we see that our background energy should also be changed. Let's change the peak energy to 509. And let's change our background energy to 517. Once again, an excellent demonstration of the need for the test acquire. We now have the correct peak and background energy for oxygen. Let's go to our next element using soft key number 5. That will be our chromium peak. And let's test acquire soft key number 1. Now we see a similar situation. We are getting interference with the chromium peak from the oxygen peak. Thus, it's difficult to determine the exact maximum energy for chromium because the maximum energy actually coincides with the oxygen peak. We see that our background energy, where it is selected, is a good energy selection of 550, no interference with any peaks there. What we need to then determine is the exact center for the peak of chromium. To do that, we can leave the peak energy at 525, and let's use a smaller acquisition width. Once again, let's try 20 volts. Change the acquisition width, function key number 3, and use a width of 20, and reacquire using soft key number 1. We now see that the maximum counts does coincide with the maximum peak energy for chromium, telling us that the energy should be set at 523 rather than 525. Press function key number 1 and change that energy to 523. We now have the proper peak and background energies for the chromium peak. Let's go to our next element, which will be copper, and begin the test acquisition, soft key number 1. We do not see any signal, but notice that all of our peak energies are labeled 916. Looking at the acquisition width, we see that that was set at 0 in the element table. That should be set at a width of probably 50 electron volts. We can change that by pressing function key number 3, changing the width to 50 volts, and reacquiring the test acquire, soft key number 1. We see that the peak of copper is at 916. That is the center of our copper peak. Notice that the signal is very, very small, and because of that, it has expanded full scale bringing the far right energy being 941 to the very top. What we need to do is probably collect this data over a smaller range. It looks like our background energy should be somewhere closer to 920, right in between 916 and 928, maybe 923 or 924. So we can use an acquisition width, function key number 3, of about 20 electron volts again. And we can then reacquire pressing soft key number 1. Notice that if we have low signal or no signal at all, once again, that is the disadvantage of a 2-point or a 3-point profile. In this material, we are lucky because the substrate is copper, and we see a little bit of that copper on the surface. If we saw no copper on the surface, there is no way in the test acquire that we could set up for the peak and background energy for copper, because none of it is present. What we would have to do is trust the peak and background energy as set up in the tables mode. So again, that is a disadvantage of the 2-point or 3-point profile. Any elements that are not on the surface are very difficult to set up for. Whereas in the window acquisition, we can set up for those elements with a wide window, and it doesn't matter how that peak shifts if the energy is not exactly where it should be. If there is a 4 or 5 volt shift, with a wide enough window in window acquisition mode, we will still be able to evaluate the data and obtain valuable information. If we set our peak and energy incorrectly for copper, once we get to the copper material, in this case that being the substrate, it's very possible that we would get no indication of copper present, because the peak minus background could either equal 0 or be a negative number depending upon where we choose the peak and background. Again, 2-point and 3-point profile advantages are they are very, very fast. You can get very good signal to noise, and they can be done very quickly. If you have thick material, it's nice to be able to quickly sputter through them. But you need to know the peak and background energies are set up correctly in the element table mode. That we have access to through the semi-permanent commands. We can see that our peak energy is still at 916, so that is the proper peak energy, and it looks like the background energy should be 923. We can change that with function key number 2 and background energy of 923. We have now finished the test acquire in setting our peak and background energies for carbon, oxygen, chromium, and copper. At this point, we are ready to acquire the 2-point depth profile. We already have our ion gun on and set, so we can press soft key number 6 and begin the acquisition. Since we acquire the data much faster, we will get many more data points than we got in our first profile. Remember, 20 minutes for our first depth profile gave us 42 data points, including the first 2 pre-sputter data points. Now you can see that every time the color moves for the carbon or chromium or oxygen, those are all data points. Maybe what would be more informative is looking at what cycle we are on. Right now we are on cycle 12, and it has estimated that the total number of cycles for the 20-minute profile will be 423 cycles. That's 423 data points per element. Again, on the window profile, for the same amount of time, we were set for 42 data points. We have a factor of 10 more data points using the two-point profile mode. We can also see that we have baseline resolution, meaning that when the carbon peak is gone, it drops to the exact baseline, meaning that the peak minus background is either 0 or a negative number. Same way with oxygen. We have a little bit of oxygen in the beginning, but once we sputter through that oxygen, we find it dropping to 0, meaning peak minus background is either 0 or a negative number. Notice also that we do not have a soft key that allows us to display the region. We are no longer looking at regions. Regions correspond to windows. We do not have windows. We are looking strictly at a peak and a background, and it is going much faster than the window profile. To further demonstrate the speed, let's take a closer look at the element label and the region number corresponding with that element. Notice how quickly we go through the elements, spending most of the time on carbon. The element label displayed is the last label drawn, so it draws the copper, and while it acquires the carbon peak, it sits longest displaying the copper peak. Notice that we very quickly go through carbon, oxygen, chromium, and copper, much quicker than in the window profile mode. We have now completed the 20-minute depth profile using the two-point mode. To display that, we use function key number 16, which is display last acquisition. Once again, we want to look at this profile, profile 302, and we want to look at it in the all regions and in the profile mode. Pressing soft key number 1 allows us then to display that profile. Because of the number of data points, we see a little bit more structure in the oxygen before it disappears from the surface of the chromium. We see the interface between the chromium and the copper. Because the peaks may have shifted slightly, we do also see some structure at the interface, both in the chromium and the copper peak-to-peak heights. Those are difficult to interpret at this point because we cannot look at the windows and find out whether the peaks actually moved. We can only believe that the peak minus background somehow changed a little bit here and a little bit here on both the chromium and the copper. Another point to make is we did this profile in the continuous profile mode. The time that it took to acquire this data was 21.7 minutes that we see at the bottom of the graph. In our window profile, the sputter time was the same, approximately 20 minutes, but the time that it took to acquire that data was much longer than 20 minutes. I believe it took roughly 40 to 50 minutes for that data because, again, we used the alternate profile mode. The sputter time was the same, but we were not collecting data during the sputter time, so that took extra time to collect that data in between the sputtering. We did sputter for 20 minutes, as here we have sputtered for 21 minutes, but our data collection in the continuous mode the time is the same as the total sputter time. So once again, we mentioned the differences between the point profile mode and the window mode, and also here I want to point out the differences between the continuous and alternate profile. The continuous profile being that the data acquisition time will be the same as the sputter time, whereas in the alternate mode, the sputter time will be the actual time that we sputtered the sample, but the acquisition time must be added on to that, the acquisition being alternately collected when we were not sputtering the sample. What we would like to now demonstrate is the suspend acquisition mode of a profile. What we will do is we will find another area on the sample that has not been sputtered and set up for a window profile. What we would like to do is suspend the profile at this interface and take a full survey scan. That can be very helpful in determining whether at the interface we have contaminants that we were not following in the original profile. So again, what we will do is we will exit from this mode by pressing soft key number 8. We can then clear the screen holding the control key and pressing clear. We have now found another area on the sample that has not been sputtered. We have once again positioned it at the focal point of the analyzer, and we have the same electron gun parameters that we had before, that being 10 kV and 3.43 microamps of current. Since this is our third area, let's again enter the file naming. What we would like to do is, again, we can keep the sample prefix as PRO. Let's change the start file number to 401. And we can keep the comments the same because it is the chromium on copper sample. Let's exit our file naming menu. Once again, we want a survey to determine what is on the surface, if there are any new contaminants. Again, we have the survey parameters set from last time, so we can press function key number 5. From the N of E spectra, we see that this looks very similar to our first area in that we do have some silicon on the surface. We see the low energy silicon peak here. We also have more copper on the surface than we had on the previous area. And here we see the high energy silicon peak, which we did not see on area 2. This survey scan is set up to take 5 minutes. we can see from the signal to noise that we probably do not need to acquire for a full 5 minutes, which would be a total of 10 cycles. We are on cycle number 4. What we can do is cycle stop the data acquisition. We can do that now on cycle number 5, which would be 2.5 minutes of data acquisition. To activate cycle stop, we press soft key number 2. That will now stop at the end of this cycle. We can then evaluate the data. If we do not have good enough signal to noise, we could take more data, signal average, to this file, being PRO 401, by utilizing the more key, which would be function key number 12. Let's evaluate this data. To redisplay that, we use function key number 16. We'll display our last acquisition. We then want to differentiate that, so we can press the data massage key, which is soft key number 5. And to differentiate, we use soft key number 7. What we see here is the low energy copper peak, low energy silicon peak, possibly a little bit of sulfur. We also see carbon. These peaks are probably titanium peaks. We then have chromium, oxygen, copper, and silicon. Now that we have evaluated what is on the surface, what we would like to do is set up for the window profile so we can demonstrate the suspend routine. To do that, let's first clear the screen by holding the control key and pressing the clear key. We now want to set up the profile, so we can hold the shift key and press function key number 7. This time we want to use the same parameters that we used, that being the window profile, file name PRO202. So let's press function key number 1 to file. We can then hit enter. It now asks for the file name, and we want file name PRO202. Automatically, we have the exact parameters that we used when we acquired the profile PRO202. What we can do at this point is add a region for titanium if we want to follow titanium through the sample. Let's do that by pressing soft key number 1. Add the titanium. There may be a slight overlap with the chromium if we use the second titanium peak, so we will use the TI1 peak. Once again, let's not use narrow acquisition, but wide acquisition, so we will say no to narrow acquisition. Since that is a small peak, let's also go 10 sweeps. Function key 11, and number of sweeps 10. We can now go to our next menu. We are set up sputter time of 20 minutes, number of cycles 40. These are exactly the parameters that we used for profile 202, alternating sputtering, sputter intervals at half minutes, saving every energy region, region display N of E, 5-point differentiation, analysis area full, and EMS routine sample. We already demonstrated the test acquire, and we are convinced that our windows are set properly. We can at this point acquire the profile by pressing soft key number 1. Again, the first 2 cycles will give us a baseline. We are not sputtering, but we want to know what the level of all of our elements are before we start sputtering. We do that by taking 2 pre-sputter cycles, and then we begin our sputtering. What we see is carbon was on the surface, and as we have now sputtered 2 cycles, which would be a total of 1 minute, we see carbon decreasing. Silicon was also a surface contaminant. That is decreasing. Copper was at this point only on the surface. We know it's the substrate, but we did have some on the surface that is decreasing. Chromium is increasing. Oxygen is also increasing. Probably the oxygen is increasing because the carbon was masking it on the surface. We are now removing the carbon, seeing a chromium oxide layer, and we will probably be sputtering through the chromium oxide layer into the chromium layer. We can see here that on cycle number 8, we have already reached close to the interface. Chromium has started to come down. Copper has started to come up. It is at this point that we want to suspend the profile so that we can acquire a survey scan at this interface. We are now at cycle number 9. We discovered this was happening at cycle 8. We are now on cycle number 9. When we suspend acquisition by pressing soft key number 7, it will complete this full cycle, that being cycle number 9. It will then blank the screen and return to home bank. At that point, we can take survey scans, multiplexes, maps, or line scans. For this demonstration, we will only take a survey scan in order to determine if at this interface we find any new contaminants. We have now suspended the profile. Notice that on the home bank we have a new key, which is soft key number 4, that says return suspend. That will return us to the suspended profile when we are finished with the acquisition that we wish to accomplish at this point. I mentioned we now want a survey scan. Again, we are all set up with survey. We have the proper parameters. So we can begin survey acquisition by pressing function key number 5. Notice that the file name is PRO403. PRO402 is our profile, and PRO401 is our survey scan from the surface of this area. In the N of V mode, we are seeing the low energy copper peak, we see the chromium peaks, and the higher energy copper peaks. At this point, I do not see any contaminants. I do not see the presence of any oxygen, any carbon, or titanium. But again, to fully evaluate that, we need to differentiate the survey scan and look at it in more detail. Also, the signal to noise looks good, so we will not spend the full 5 minutes or go the total 10 cycles. As we did with the survey scan, let's do a cycle stop at cycle number 5. This can be used to evaluate what is happening at the interface. We cannot, if we found new elements, we could not add them to the profile, nor can we delete any elements from the profile. Once we have the windows set up for a profile, we cannot change them. So we will return to the profile with the windows that we have already set up. Again, we cannot add any or delete any. We are now on cycle number 5, so by pressing soft key number 2, we can stop at the end of this cycle. When it is complete, we return to the home bank. We could return to the suspended profile, but let's first take a quick look at the survey scan. Again, to display the last acquisition, we press function key 16. We can then massage the data pressing soft key number 5, differentiate with soft key number 7. Taking a close look at the differentiated data, we see the low energy copper peaks, chromium peaks with no titanium, no carbon, no oxygen, higher energy copper peaks, and no silicon. To return to the profile, let's first erase the screen holding the control key and pressing the clear key. We also need to get back to home bank, which is holding the shift key and pressing function key 21. To return to the suspended profile, we press soft key number 4. The computer responds with the question, do you wish to use these EMS settings? It's very critical in a profile that we use the same multiplier voltage. At this point, if we were to say no, the computer would reset the multiplier voltage and the profile would look discontinuous. So we want to make sure at this point to answer yes, we want to use the same EMS settings, and enter. We have now returned to the profile. The first thing that happens is it will sputter. In a cycle, we sputter first, then we acquire the data. At this point, it is sputtering, and now we begin data acquisition. Notice that we continue from where we suspended. We have a continuous and an uninterrupted profile. As I mentioned, if we would have said no to EMS routine, the multiplier would have been set differently, and we could have had a discontinuous looking profile. What has just happened is the copper peak increased so high that it had to rescale all of the displayed data. To do that, it erases the screen and redraws all of them on the same scale as the copper peak. Once again, the ability to suspend a profile and acquire either survey scan, multiplexes, maps, or line scans is very powerful. When we get to interfaces, we're not sure what elements are present and what elements are not present. Taking survey scans or maps and line scans can provide added information which can help us resolve the problem. We see on this profile that at cycle number 15, our copper peak has leveled off. We know from the previous profiles that once we get into the copper, we do not see any new things happening. There's no need for us to go a full 20 minutes on this profile. So what we will do is at cycle 16, we will terminate the acquisition. To do that, we will utilize the cycle stop command by pressing soft key number 2. We see now that our present cycle is cycle number 16 out of a total of 16. That means that we will continue the acquisition through this cycle, looking at the carbon peak, the oxygen peak, chromium, copper, silicon, and titanium. At that point, the acquisition will be complete and the profile will be stored under the file name PRO402. Let's briefly review what we have accomplished so far. On the microwave transistor, we acquired Auger survey scans over several areas. From one of those areas, we multiplexed and determined the atomic concentration. On that same area, we then mapped for the 3 major elements, gold, tantalum, and silicon. We also selected several line scans and acquired line scans for gold, tantalum, and silicon. We then introduced a new sample suitable for depth profiling. On several areas of that sample, we demonstrated the window depth profiling, the 2-point depth profiling, and also how to suspend and acquire survey scans at interfaces. This concludes the section on Auger data acquisition.